So, good afternoon. I am Krishna Kumar. Welcome to Krishna's classroom. We look at another topic in related to ODE. We have already looked at in detail how to solve linear differential equations with constant coefficients. I don't claim that in all cases you can exactly write down the solutions. There are a lot of problems that come. We also introduced methods of Green's function and method of variation of parameters, and we looked at the relation between them in the case of a second order differential equation which is of some physical relevance, second order linear differential equation which whose by comparing the Green's function associated with the problem and getting solutions using the method of variation of parameters. Now what we look at is the following. Now, as I told you in the beginning itself, that a theory for differential equations was sought after because it is impossible to solve in general a differential equation, except that in some specific cases one is able to solve the differential equations and write down the solutions. After all, our objective is to know the solutions of the differential equation, and it is essentially an inverse problem. What is given is a relation connecting the function, a function and its derivatives, and then you want to find out functions which satisfy the particular relation. Now, this is the basic problem, and in general it is not possible to solve it. However, there are several cases where you can solve the equation, like the equations with the constant coefficients. At least you can propose a very general method. All linear problems we can give a very general method. However, whether you can exactly solve them is a different question altogether. In any case, the physical problems ഞാനേ പിന്നെ വിളിക്കാം. ഒരു മണിക്കൂർ കഴിഞ്ഞിട്ട് വിളിച്ചാൽ പോരെ? ഞാനൊരു 2 മണിക്കൂർ ഒരു ഏതാണ്ട് 2 മണിക്ക് വിളിക്കാം. ഓക്കെ, ഞാൻ ഇപ്പോൾ കുറച്ച് പണിയിലാണ്. ഓക്കെ, റൈറ്റ്. ഓക്കെ, റൈറ്റ്. ശരി. ഓക്കെ, റൈറ്റ്. So, as I was telling, it is not easy to find or explicitly solve differential equations. However, we would like to see whether the properties of the solution can be read out from the properties of the relevant functions appearing in the differential equation. Now, this is how the theory has been developed. And you see that for all linear equations or linear systems, you have a very credible theory where extensive use of linear algebra has allowed us to make deep inroads. Although still we cannot claim that given a linear differential equation you can explicitly write down the solutions of the equation. So, this is where we stand at the moment. So a theory is very much called for, and the art of knowing the solution without really explicitly seeing it is essentially the purpose of a theory for ordinary differential equations. Now, having done or having extensively looked at the linear equations and linear systems, we now try to look at the special case which is relevant to physics, that is an autonomous system of linear or not necessarily linear, autonomous system of differential equations, and the so-called singular points of the system. So this term we will be explaining what exactly it is. Now let us consider two dependent variables. Okay, it's a first order system with two dependent variables. That means there are two simultaneous differential equations, and we write it in the form, and whatever we say can be generalized. Almost everything can be generalized for systems with more dependent variables. So let us consider the system dx by dt qxy, where x and y are dependent variables, t is the independent variable. So x comma y are dependent variables, or what you call the unknown. And t is the independent variable. Our problem is this: given p and q, the relation connecting the derivative of x, derivative of y with respect to t, and x and y is given by the system 1. Our question is, find the exact dependence of x and y on the independent variable t. This is what I said, it's not often possible to solve these problems. It depends on how simple or how complicated or how simple P and Q are. If they are simple enough, possibly one can exactly solve them. Otherwise, it is difficult. Okay. As I said, you can think of more number of dependent variables, say x1, x2, etc., xn, and then talk about systems. Here we assume the following: 1. P and Q are functions of x and y and does not and do not depend on the independent variable independent variable t. That's the assumption that we are making. Independent variable t explicitly. Such a system is called an autonomous system. So we have defined what an autonomous system is. Here P and Q do not depend on T explicitly, but it depends only on X and Y. Now, second assumption that we make is the following. P and Q are continuous. See, they are functions, they are real valued functions from, so P is a real valued function from some domain D contained in R2 R, we are assuming it is continuous. So also Q is also a continuous function defined on D. Both are real valued functions. We are assuming. So as a map from a part of R2 to R, we are assuming the function is continuous and with respect to both the variables. That's one assumption. The third assumption that we make is the vector Pxy Qxy is satisfies a Lipschitz condition with respect to y. Okay. Now, this of course means you recall the following, that see, what you have is this norm of this is the assumption that we are making. This is what where K is called the Lipschitz constant. Now this you refer back to what is Lipschitz constant. Here you see that T is not coming into the picture. Otherwise what happens is, see, generally this is the case. T is the independent variable is involved. This is a more general scenario. This system is not an autonomous system. We say that P and Q satisfies the Lipschitz condition if this vector is less than or equal to k times norm of xy minus norm of x tilde y tilde. Okay, but t is not involved in that discussion. Okay, so this is what you call the Lipschitz condition with respect to x and y, that is this is the assumption that we are making. And which is equivalent to saying that P is Lipschitz with respect to xy, Q is Lipschitz with respect to xy. Now that is, of course, we have seen in the beginning that if you have a, because you see that this is a vector valued function of, so this is this, you see this PQ is a map from D to R2. So P is a map from D to R, Q is a map from D to R, where D is a domain in R2. So this is equivalent to saying that both P and Q are independently Lipschitz with respect to xy. Okay, so that is these are the three assumptions that we make, right? So we assume the system is an autonomous system, by which you mean that P and Q are not dependent on the independent variable t explicitly, and then we assume P and Q are continuous, and we assume that P and Q are also Lipschitz with respect to x and y. This is the assumption. So this is sufficient to help us assert the existence of a solution. Existence and uniqueness solution of a related initial value problem This is the existence and uniqueness theorem, application of the existence and uniqueness theorem. What does it say? Suppose we consider the initial value problem, one with the, or I will write it explicitly, dx by dt and for some t naught, we have x t naught equal to x naught, y t naught equal to y naught, where we have the following assumption, namely that x naught y naught is a point of D. So what we are assuming is that there is some point in D, say x naught y naught, which is chosen as the initial values for x and y at time t equal to t naught. So let us just write down. Now once I give the geometric picture, it will be clear what exactly we mean by solution, and we also look at some specific examples so that you get an insight into the problem. Okay, let us, yeah. It's a point in D. So this is what you have. Suppose this is the x, y plane, and this is D. This is the boundary of D. It may be bounded or unbounded or partly. Okay, so we are not making any assumption at the moment. And x naught y naught is a point given here, and this is given as the initial data for your solution. That means if you plot the curve corresponding to the solution, then it passes through the point x naught y naught. Okay, let us look at the geometry of the problem. So this is the initial value problem. So we call this initial value problem, denote it by 2. Of the system 1. Then existence and uniqueness theory asserts that there exists an interval I with t naught belonging to it, such that and they are differentiable functions with a continuous derivative, and dx by dt for all t belonging to I. So it says two things. One, there is an interval I containing the point t naught such that, and functions xt and yt defined on the interval I such that dx by dt equal to p xt yt, dy by dt equal to q xt yt for all t belonging to y. Secondly, xt naught is equal to x naught, yt naught is equal to y naught. That means the functions xt, yt satisfies the differential equations or the system of differential equations and the given initial data. Only one and only one such function exists. Okay, so that is the uniqueness part. And this is guaranteed by the assumptions that we have made, namely P and Q are continuous and P and Q are also Lipschitz. This is the consequence of the existence and uniqueness theorem. Okay, so that we have assumed. Now we also make some more remarks about, because we considered the problem on what is the largest interval on which such a solution can be defined. Because if you recall the proof of the existence and uniqueness theorem, you see that what we have done is purely, local existence and uniqueness theorem. What we assert is that there is an interval surrounding t naught where a unique solution exists of the initial value problem. Okay, but on how large an interval this takes place. So that's the next question. So we make some statement about this. How? This is the question that you are asking. That's the question that we are now taking up. Okay, let us make some statement about this. And then we go for the geometric picture of the problem, which will make things more clear. And later on, we will also look at the physical interpretation of the problem. So that will make things very fascinating. Okay. So before that, we look at the largest interval on which the solution is said to exist. So what are the possibilities? The answer to this question is that the first one, the solution may be defined. Okay, let us look at for t greater than. We first take up the case for t greater than t naught. The first statement that we make is that it is defined for all t greater than or equal to t naught. Okay, or two, the possibility is this. This is not always true. If the solution is not defined, for t greater than t1, say. Now we are assuming t1 is also greater than t0, okay, for the time being, and I'll make a statement for t less than t0. then what we can say is the following: either A as t tends to c, as t1 minus 0, either xt yt, the point approaches the boundary of t, or what can happen as t tends to either xt or yt or both become unbounded. Okay, so there are two parts for the statement. Either it is defined for all t greater than or equal to t naught, that means on this interval t naught to infinity it is defined, or it may not be defined there, then it is defined for t naught, t1 with the property that as t tends to t1 from the left, that is t tends to t1 minus 0, xt and yt may approach the boundary, because as I said there is a boundary, so the solution may be having the property that it just gets closer to the boundary. It doesn't say that the limit exists, okay, it doesn't say that the limit exists, but the difference between what you can say assert is that if you take an arbitrary point on the solution and compute the distance from the boundary, what you say is that this distance will go to 0 as t tends to t1 minus 0. Or the other possibility is that this t may just become unbounded. So it may be defined only for up to say t equal to t1, so that as t tends to t1 minus 0, either xt or yt or both xt and yt become unbounded. Now these are the various possibilities. In other words, what you can say is that there is a t1, this may be infinity, so that this is the maximal interval on which the solution is defined to the right of t naught. Now we can make a similar statement. T1 to T2 to T naught to the left of T naught. What will be the corresponding statement? This T2 is minus infinity. Okay, that means for all values of t which lies between minus infinity is, so T2 is minus infinity, or what you have is that as t tends to t2 plus 0, what you can assert is that xt yt approaches the boundary of D or again the possibilities are xt yt or both. Unbounded as t approaches so that means the following: t2 t1 is the maximal interval, or what we are asserting is that there is a maximal interval say t2 t1 on which this unique solution is defined. So this means the following: t1 where t2 may be minus infinity, t1 may be plus infinity, and t0 belongs to t1 such that the unique solution so that's about the existence and uniqueness of the solution. So without any inhibition at this stage we can talk about the solution defined on the interval t1 to t2. Okay. Now we make some further remarks. So let us look at the geometry of the problem. So we consider the differential equation. The differential equation is characterized by the functions e xy qxy on some domain R. D is an open connected subset of R. That's what we mean by this. Okay. What interpretation we give this? So suppose this is the geometry. Suppose this is D. This is X. This is Y. And P is defined on this. Now assume this is the point XY. Now Pxy, Qxy, so let us write this as a vector. Let Vxy Qxy. Then V is a vector whose components are P and Q. P and Q. And you know that gives a direction. So you have a direction here determined by PQ. Okay. Now our assumption that this is an autonomous system tells that for all the time t, this direction is the same. Okay. So the system is autonomous. So what is happening? At every point of D there is a vector PQ defined. So that's the interpretation that we give. So what we have is this. Which we assume, and V is continuous and of course satisfies Lipschitz condition. Let us not bother about it. And Lipschitz. So what you have, this does not depend on t. First of all, the problem is this is the system is autonomous, which implies P and Q do not depend on T, do not depend on T explicitly. Which means that for all the time the direction PQ at XY is the same. That is, for every t, the direction V Now this is the important part. That is what we mean by it is autonomous system. So what do you have now? So at every point there is a direction. Now what you have? Now we have a field of directions at that is a differential equation. So the differential equation is defined by the field of directions. Now this is the geometric interpretation. Okay. Now what is that we are looking for? We are looking for a curve. So what we call a solution is the set of points xt, yt for t belonging to t1 such that which is D, which is a curve in D such that the tangent to this curve given by x derivative of t, y derivative of t is the given v at yt. This is what you mean by a solution. And what we assert is that once you fix a point x naught, y naught in D, okay, there exists a t interval, say t2 t1, which contains the point t naught, and such that the curve is defined, a curve is defined on the interval t2 to t1 given by xt yt with the property that x prime t y prime t, the vector x prime t y prime t is essentially vxt yt. Now this is such a unique curve exists. Now this is the importance of the existence and uniqueness theorem. Now that is the geometry of the problem. Okay. So what you have is that you are now searching for a curve whose tangent is given by, at this point is given by PQ. Okay, let me give an example. It is nice to always look at some example. Let us can start with the most simple situation. Okay. So let us look at some examples. First example is some AB. Constants. And B are constants. So what do you have? Let us picture the whole thing. Now assume D is equal to R2. Then you see that, suppose this is the point xy, there is a constant direction. It's all governed by this vector AB. This is the point x1. So what you have is that at every point there is this, these are parallel vectors. So geometrically you can immediately write down what the solution is. What is the solution? It's quite clear. It's a line so the solution is given by a straight line in the direction so the set of the so all solutions are by parallel lines given in the parametric form plus where x naught y naught is a given point. Now this you can immediately check, it's a solution of the problem because you see that x derivative of t is equal to a, y derivative of t equal to b, therefore we are writing x derivative of t, y derivative of t, this is the equation. It's the vector, this is the differential equation and you see that if x naught y naught is a point in D, then you are having at t equal to 0, x0 equal to x naught, y0 equal to y naught. Okay, so the solutions are essentially all lines of this kind, all parallel lines. They are the solutions. Okay, so that's a very simple problem, but it carries all the insight into the problem. So we go for a slightly more complicated example. Consider only autonomous systems. That means we do not see what is happening is that if this V is also dependent on t, then it will be changing direction with time. Okay, that will be more clear when we look at the dynamical interpretation. Okay, so what do you get? Here what one gets is, so let us look at the second problem. Second problem is, I take Vxy to be equal to xy. Okay. Now what do I have then? See, I am taking a point xy. So this is the direction of xy. So what I have is this. Here I have a vector whose length is as long as the distance from here to xy and in the same direction. Okay, so this is the vector that I have. So if I take this point, so this point, then if this is your xy, then you are going to have a direction like this. So if I take this point, then the direction is this. The vector is this. If I take a point here, then the direction is. So you see that this is radial directions. So you see that they are all radial directions. Therefore, what are the solutions that you have? Like in this specific case, we can immediately write down what the solutions are. The solutions are given by radial lines, radial lines, zero. Of course, 0, 0 is not included as it is. We have not, because the differential equation it is 0, 0 there. Of course, you can, if you want, you can include this. But these are all radial lines that you are defining. So all radial lines give you this. And let us see what happens if you solve this. dx by dt solve it. So what do you get? xt equal to x naught e to the power t or if you want you can write this as t minus t naught. Now you can immediately check that x derivative of t equal to x. Yt. And you also have the initial value xt naught equal to x naught, yt naught equal to y. So this defines all solutions. Okay, right? And there is some problem at 0, 0 that we will not bother. So you have all radial lines giving you solutions of the differential equation. Now that's also easily predictable. So let us take the third case. This is again another autonomous system. Third case is where we assume vxy minus yx. So the equations are Now this is a bit more sophisticated than the examples that we have looked at. But the geometrically we can try to resolve this easily, and then exactly it is not a problem. You can solve these equations because this is of the form that is d by dt of this is equal to 0 minus 1 1 0. This is the system that we are looking at. Okay, this is a system with the constant coefficients. One can solve this easily, but let us look at the geometry of this. The geometry of this problem is the following. Let us take the xy plane. Take any point xy. It's a smooth function. It's a smooth vector valued function. Now at xy we are placing a vector whose components are minus yx. What is minus yx? Suppose this is the vector xy, then minus yx is what? First of all, you observe that minus yx is orthogonal to the vector xy. So it is in this direction. Either in this direction or in this direction. Okay, because the dot product of xy this is the dot product, this is equal to 0. Therefore, Vxy is orthogonal to the radial vector xy. Okay, so it is in this direction and placed at this point. That is the base point for this vector. So I will do that. So first of all, let us decide whether minus yx. Okay, let us take a point in the first quadrant. First quadrant, what happens? For instance, let us take 1 minus 1, 1, 1. What is the vector? The vector is going to be minus 1, 1. Okay. So minus 1, 1 is in the second quadrant. Therefore, you see that if xy is in the first quadrant, then it is going to be in this direction. This is minus y x. Okay. Right? So you take some vector here xy, then it is going to be orthogonal to it, and in this direction. And if it is here, then it is going to be like this. So the length will vary, depends on the point xy. And you see that if it is here, then it is going to be something like this. Always these angles are orthogonal. So now you see it defines a field of directions. What are the field of directions? The field of directions defined by minus yx is orthogonal to the radial directions. In which way? In the counterclockwise way. It's not clockwise. It is in the counterclockwise way. Okay. So Vxy defines a field of directions orthogonal to the radial vector the counterclockwise direction. Now one can easily guess what the path is. Now we observe that all the solutions are as concentric with center. So the solution space is, so the solution, if you draw the or make a plot of the solutions, they are going to be this. These are the paths, circles, concentric circles. Okay. So if you take a specific point x naught, y naught, then it's a circle with a radius x square root of x naught square plus y naught square. Okay. So that is going to be, so a solution T naught is given by and write x square plus y square so it is, these are the circles that you get. So through every point there passes a circle, a uniquely determined circle. Now what you get is that this is defined for all t from minus infinity to plus infinity. But what happens is, its concept, if you take an individual path, the property of the path is that after some time it returns to x naught y naught and then keeps going. So the paths are just these concentric circles, but the dynamics is quite interesting because it corresponds to particles moving in along these circles in with the period given by the time that it takes to go around. That's easy to work out. It's quite easy to work out. You can solve this equation. You have to solve this equation, that is dx by dt I leave it you to solve these equations. It's quite easy to solve because what you do is, if you take the second derivative here, that is going to minus dy by dt. Minus dy by dt is equal to x. Therefore, you get d2x by zero. Now you can find the solution of that. So you see that sin t cos t or e to the power it will come two complex solutions, e to the power it and e to the minus it will be the complex solutions that you get, and from that you can find out what xt yt is. I leave it to you. Okay, so the solution is essentially given by the following. Equal to I'll write it this way. The solution is given by a linear combination of this. So xt yt is given by a cos t dx by dt equal to minus sine. Okay. Where a and b are arbitrary constants with dy by dt equal to so dx by dt equal to minus sin t, which is y, dy by dt equal to cos t, plus b into dx by dt is equal to minus cos t y. Okay. dy by dt equal to this. Now you see it, at t equal to t naught it passes through the point x naught y naught, so you can calculate the solution. Okay, so this gives the general solution. This is the general solution. You can work out all specific solutions by giving the initial data. So this gives some insight into the problem from the geometric point of view. So these three examples will give you some insight. But there are more complicated examples can be found out and even plotted. So you can actually work out. See, what is happening is this. See, the field corresponding to this problem is this. This is the field that is described. And so on. So similarly, you see that everywhere on this line it crosses like this. So you have field like this which together form the curves like this. So that's quite easy to work out. So I think you would have got the idea. Okay, let us look at the dynamical situation. before that, let us make some simple observations. If Qxy, and with all the assumed conditions, and then x is also a solution. It's not the initial value problem I am talking about. It just satisfies xt yt satisfies the equation, means xt plus tau, where tau is a constant. And that is probably very easy to work out, because what you do is, suppose, let me write and what you have is dx1 by dt equal to for everything, some interval time. Now let x to t okay. So let us write down dx2 by dt, this is equal to dx1 t plus tau dt, which I can write as dx1 t plus tau But what is this? Suppose I write this as, now choose tau is a fixed constant. Okay. Then what you have is this dx1 by ds this you have. Okay. Therefore, this is equal to tau. Okay, this comes from here. But what is this? x1 t plus tau is x2. Therefore, we get dx2 by dt p of similarly. Therefore, if x1t and y1t satisfies the system, then x2t and y2t also satisfies the system, where x2t is equal to x1 t plus tau so that's what we infer. This is because it is autonomous, otherwise it is not satisfied. Okay, you know that if T is explicitly involved in it, in both P and Q or in one of them, then you see this is no more valid because all our computations will not be justified. Equation 1. Okay, and this is remark okay, so that is a result that we are really interested in. Okay, so we shall just use this later. Before that, now I make another remark. If D prime then on D prime so this is something like y, you can treat y as the dependent variable and x as the independent variable. Okay, and then So it's a first order differential equation with y treated as a function of x, and then you can work with that first order equation. Okay. Now I think this is the right place. I think I stop, and now I will introduce the notion of what are called the characteristics, and then go on to give the physical interpretation of the problem. So thank you very much.